All right. So for the rule of OR, generally we're talking about a single event and either of two outcomes occurring. Now we're talking about multiple events. So for these questions, all of them, we're talking about two cards being selected at random. Right. So what we have to start doing is thinking about what is it really asking me to do? So for number 3, two cards of the same suit would mean we're looking at the probability of getting a heart and a heart, or a diamond and a diamond, or a spade and a spade, or a club and a club.
Same suit means same set.
Yeah, same type of card, yeah. And as long as you know how many cards are in each suit, which you would, because I would give you the sample space for a deck of cards, you're in good shape because it's just a matter of counting, right? There's 13 of each suit. So we're starting off with 13 out of 52 as my probability of getting a heart. All right. So in probability, we always assume success. We always assume that we achieved the objective. So I got the heart. Now I just want to know the probability of getting a second heart. Well, I didn't replace the first card before I selected the second one. So I randomly selected a card from a deck. Turned out it was a heart. Didn't matter what kind of heart. Threw it away. How many hearts are available now? 12. How many cards overall? 51. All right, so that's going to give us a product of 156 over 2652. All right. So 156 over 2652. So that's the first scenario. So that's this case. The second case, now there is a shortcut to this, but I want to at least use this problem to help us discover the shortcut, and then after that, we'll just use it. So, OR is like a reset button. We're starting over because it's either of these situations or any of these situations occurring. They wouldn't all occur at the same time. So let's say it wasn't the hearts, it's the diamonds. So if that's the case, I put all the cards back in the deck, randomly select one. The probability that it would be a diamond would be 13 out of 52. Same scenario. Take a card out of the deck, it turns out it's a diamond. All right, cool, throw it away. Probability that the second card selected would be a diamond would be what? 12 over 51. Right? It's the same thing. All right, so we're kind of on to something here. We're going to get 156 out of 2652 again. So that's telling me that for the next calculation, I probably should be expecting the same thing again. All right, so 13 out of 52 and 12 out of 51 for the same outcome. 156 out of 2652. And for the last one, the same outcome as well. All right, you could show the computations, but we know based on the relationships, based on the trends that we're seeing, that it's amounting to the same thing, so why bother, you know? Why did that hop that way? Oh, there it is, little extend page. All right, so then because it's addition, based on the fact that there's or in the problem, or means add, all I have to do is add up my numerators. All right, so this time I will use the highlighter on purpose. Because common denominator is already in place. That's why I encourage you not to reduce fractions. All right, so we're looking at 624 over 2652, and that would be my probability. Now, you may consider converting it over into decimal form just to get a feel for it. You know, because like, let's say I was on my way to a casino and I wanted to figure out some probabilities. You know, passenger in the car, like we talked about. 624 over 2652 might not have a whole heck of a lot of meaning for me, but the decimal equivalent, I would be thinking in terms of percent. What are my chances of winning? If I could say now that we're looking at like 30% chance of winning, that means more to me than 624 over 2652. All right, so for your own benefit, you might consider turning it into decimals, but I'm never going to ask you to do that. All right. So that's going to streamline the last one significantly, like significantly. Two cards with the same value. So probability, that could mean probability of getting a 2 and a 2. Or maybe it's a 3 and a 3. Or a 4 and a 4, 5 and a 5, 6 and a 6, 7 and a 7, 8 and a 8, 9 and a 9, 10 and a 10, jack and a jack, queen and a queen, king and a king, ace and an ace. So, or dot, dot, dot. Or maybe dun, dun, dun. I entertain myself. That's the only way I get through life. So, what I just learned from number 3, and this squeaky chair that's really building up my confidence, is that if I figure out one of these probabilities, then all I'd have to do is figure out how many pairings there would be, and then I could just multiply. Because in the last one, if I just took that 156 and multiplied it by 4, I would have had my answer. All right? So sometimes we can figure it out just by, considering it for a second. Sometimes you have to count it out. So 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, 7 and 7, 8 and 8, 9 and 9, 10 and 10, jack and jack, queen and queen, king and king, ace and ace. Oh, 13 possible pairings. So 13 pairings. So that's what my multiplier is. Now if I just find the probability of getting a successful outcome in just one case, then I'll be good to go. So probability of getting a 2, I got a deck of cards, well shuffled, well, just shuffled, randomized. Probability of getting a 2 is 4 out of 52. I withdrew a card from a deck. Turned out it was a 2. I got lucky. Now I want to get greedy. I want to know what the probability is of getting a second 2. So I have 3 over 51. I got one less 2 available, and I have one less card overall available. So product 12 over 2652 times the 13. So we're going to take the 13, multiply it by 12 over 2652, and we're going to get 156 over 2652. All right, so it's an interesting outcome because you kind of look at the numbers. I can't help it. Sometimes the eyebrows are raised, and I see, oh, look at this, I get the 156 over 2652. That's the same as one of these outcomes over here. Any one of these, right? So what I just learned, and I didn't intend to learn this, but I just learned that it's just as likely that you will get any pair of cards with the same value, so any pair, as it is to get just one pair of cards with the same suit. So you start thinking about what's more likely to happen. And, you know, conceptually it kind of makes more sense that if I'm going to randomly select two cards from a deck, what's more likely to happen? Getting two cards that are both hearts, yeah, because I'm not looking at all of the same suit, I'm just looking at one suit. Two cards that are just hearts, or two cards that have the same value. It turns out that they're exactly the same. Right? So if I'm playing a game of poker, you know, because what happens is people, they kind of get sucked in, you know, like you have in your hand, you have a couple of spades, and then you see the flop cards, or you get a couple of spades out there, and you're like, ooh, maybe I can get a flush. So you're relying on another spade coming out, when really maybe you should be looking for a pair. You know, maybe that's the winning hand, right? But what happens is people get sucked in because they're trying to get that flush, and so they put all their money in, and it turns out that they're more likely to get a pair of matching values, and so it turns out they never get that last spade that they were looking for, so they don't have the flush, but they lose to a person that just had two pair, or even one pair. You know, and so like, how did that happen? I almost had to win, and this person had such a weak hand and they beat me. And it's because of stuff like this that allows that to happen. It's the probabilities that, you know, like I would think expert poker players, I don't know that they go home and calculate probabilities, but I would think that they have intuitive understandings of the probabilities. All right, most likely through experience, but you know, maybe they are going home and studying, you know, like self-imposed homework. That's the best kind. Like math homework because you're interested.